Everybody's time. Thanks again for joining today for our first 𝗂𝗏 organized webinar. Today we'll cut through the marketing fog around digital twins and get to the engineering truth. You'll learn how to objectively categorize digital twins, navigate marketing claims, and set a real benchmark. As I said, please save your questions for the Q&A session at the end. There will be ample time for that, or you can post anything, anytime during the presentation in the chat. So what's the background? Our in-place infrastructure is facing a profound crisis due to decades of chronic underfunding and neglect. As a matter of fact, there's one bridge collapse once every week somewhere worldwide, and this rate keeps accelerating. So are digital twins here to the rescue, or just another overhyped and under-delivering concept? Before we dive deeper, let's take a quick look at where the term digital twin actually comes from. The concept was first formalized by NASA during the Apollo program. Back then, they created exact ground-based replicas of spacecraft so they could simulate and respond to problems remotely. This turned out to be a life-saving move during the Apollo 13 mission. Later, this concept also gained huge traction in the aerospace and automotive industries. Why? Because in those sectors, the assets are mass-produced. Every Airbus A320, every BMW 5 Series, they're engineered to be virtually identical in design, composition, and behavior. So that means that a digital twin for one of those aircraft is essentially a twin for the entire fleet. But there's the problem. Our infrastructure isn't mass-produced. Every bridge has its unique story. Even if two bridges look alike on paper, same span, same design, same everything, they're not the same. Why is that? Because construction is a craft, not a copy-paste operation. Concrete pours vary with every batch and ambient condition. Material qualities fluctuate, and the local workmanship differs. So site conditions, wind, water, ground movements are never identical. Not to mention that each bridge faces its own unique environmental history. One might battle freeze-thaw cycles, another corrosion from salty sea air. So let's take a bird's eye view and look at the broadest definition of the term digital twin. So digital twin is a dynamic, real-time reflection of a physical object, not just a static copy. It doesn't just mirror your asset, it predicts and guides decisions before problems occur. Now that we established the baseline for a digital twin, let's look what a digital twin is definitely not. Everyone loves to throw around the term digital twin these days, and it's used inflationary. Pretty much anything that's digitized in bridge management can be labeled and marketed as a digital twin. But not all twins are created equal. Let me walk you through what's out there and help you to identify what can be classified as a digital twin and what is a twin imposter. First, there are digital repositories of unstructured data that collect and store inspection reports, maintenance logs, photo collections, repair documentations, scan drawings, etc. Any software that would help to organize this data is often sold as a digital twin, but it should be easy to see why that is not a twin at all. It's nothing more than a digital filing cabinet. The next level would be that this unstructured data may be organized and coordinated with a 3D or BIM model. Yes, it's definitely a step up, but it's still just digital storage of static historic data with spatial context at best. This could then further be augmented by a data dashboard that collects and aggregates sensor data from the bridge. It is certainly a valuable tool for engineers that try to assess the condition But just because you can collect a terabyte of vibration data doesn't mean you know if your bridge is about to call it quits or not. Acoustic emission monitoring can detect wire breaks. Sure, all this monitoring will inform you that something has happened somewhere, but without giving you context or impact of that event. Another approach are photogrammetric twins. Think of drone inspections using LiDAR and other high-resolution imagery, or even satellite surveillance to generate a virtual digital replica of the geometry. Yes, these platforms make accessing and coordinating of data much more straightforward. They can even detect changes over time or flag some damage early. However, they will not be able to assess the internal stress states and actual conditions of the asset. All of these methods deliver tons of data, for sure, but these twins cannot make sense of the collected data on their own. More importantly, all this collected data is backwards looking. These tools cannot answer the question at hand if the bridge is safe to operate right now, and if it will be so tomorrow in any meaningful way. Imagine administering telemedicine, diagnosing a patient over Zoom. With their camera off, you can't see them, you can't touch them, you're just guessing. That's what these supposed digital twins do for bridges. Fake twins give you a selfie when you really need an MRI. So what's the consequence? The asset owners are largely flying blind. Case in point, that sudden collapse of the statically determined 𝗂𝗶𝗴𝗶 bridge that collapsed without warning last September in Germany. I do not wish for anybody to have to walk in Mr. 𝗂𝗶𝗴𝗶's shoes. Dresden's chief bridge engineer is hardly to blame for the 𝗂𝗶𝗴𝗶 bridge calamity. He most certainly did his professional due diligence and rightfully pointed out that the state-of-the-art engineering methods were just not enough to prevent the sudden collapse under self-weight. Unlike a car engine or a factory machine, we cannot simply open up a bridge and inspect its key components. Traditional monitoring and inspections offer snapshots, but not a real understanding of what's happening inside. So what's the answer? How do we move from mere guesswork to certainty? Now, when we talk about real digital twins, we are talking dynamic, contextual, real-time representations that know the actual health of your assets, predict where and when issues might occur, support real decision-making, not just fancy reporting. Think of it as an engineer's sixth sense, only instead of gut feeling, it's based on cold, hard facts. So what is needed to that end? A high-fidelity twin needs to have these characteristics to become a full-fledged decision support system. So the representation needs to be dynamic, and you need to be able to drill down from the component level and zoom all the way out to the system or network level in the same system. You need to be able to contextualize all the collected data, and the data needs to be collected in real time. This data exchange needs to be automatically and continuously to synchronize with the actual physical state of your bridge. When you accomplish that, then you have the needed analytical basis to do predictive maintenance, damage detection, and condition-based assessments. I would also like to share a well-crafted attempt to define and classify digital twins that was presented by researchers around Professor Marx, one of the most preeminent bridge engineers in Germany. By the way, he's the guy that's heading the task force to investigate the 𝗂𝗶𝗴𝗶 bridge collapse. So here we define 3 dimensions to classify any digital twin and determine its maturity or alignment with the aforementioned criteria. One dimension is the level of detail that can be addressed, from a roller bearing over 𝗬𝗂𝗶𝗶 assemblies to the overall structure and how it relates to its environment. The other dimension is the life cycle stages that can be covered. And finally, the last dimension, the granularity of the data and degree of information that can be obtained. Most twins on the market are at maturity stage 1 and 2, and often only cover one specific LOD tier. Systems that are able to contextualize the data from the levels 1 and 2 can become predictive and flag problems before they escalate. Prescriptive twins offer more insights and help to make the right maintenance choices, and autonomous twins can then be deployed to close a bridge to traffic when certain boundary conditions are met. So this still seems to be complex and difficult to navigate when differentiating twin solutions. The good news, governments and standards are finally catching up. Real-time monitoring, predictive maintenance, decision-making support, they are not nice to have anymore. They're becoming mandatory and clearly defined. So what have we learned so far? If your digital twin can't predict, can't assess, and can't advise, it's not a twin. It's a distant cousin at best. A real benchmark twin needs real-time physical state synchronization, automated data exchange, and predictive insights. So it's not just a pretty 3D model with some motivational quote attached. So now that we set the benchmark, let's take a look how WeStatiX 𝗦𝗃 stacks up. The system is sensor agnostic and can ingest any given monitoring array. The sensor data is fused in the cloud with a finite element model that learns in real time, continuously updating itself with live sensor data and refining its model and forecast window over time. It predicts instead of merely reacting. So AI-powered simulations will anticipate failures before they happen. WeStatiX 𝗦𝗃 is not just another digital twin. It's a complete decision support engine that removes the uncertainty from asset management. The utilization factor, for instance, is right at your fingertips in real time. While most digital twins are passive information hubs, WeStatiX 𝗦𝗃 is a true structural intelligence system built to keep asset owners ahead of risk, cost, and uncertainty. We don't just build twins, we build the kind that save thousands of engineering hours, prevent bridge closures, extend the lifespan of critical infrastructure, and give you peace of mind and maybe a better night's sleep. It sounds too good to be true, doesn't it? Here's how it actually works. It all starts with multi-sensor fusion and smart data handling. Intelligent sensor management methods automatically detect and correct sensor noise and faulty signals. Edge processing and adaptive sampling optimize bandwidth and storage efficiency. Multi-sensor synchronization ensures cross-sensor correlations. The next level is our advanced structural analysis. We use operational modal analysis to determine the real-world dynamic properties without artificial excitation. Stochastic subspace identification procedures enhance accuracy by filtering out environmental noise, like thermal impacts, and will lead to very stable and accurate results. This works exceptionally well for the low amplitude responses typically in our operational conditions. And it will give us a highly accurate real-time modal tracking for early damage detection. We will further enhance the model with our AI-powered calibration with pins. Physics-informed neural networks refine material properties dynamically. Continuous inverse analysis eliminates guesswork in assessing creep, fatigue, and internal stress redistributions. Unlike traditional models, pins predict unseen conditions, giving asset owners clarity on future risks. Our actionable insights are available available on our web-based 3D dashboard. Engineers get instant visualized results with utilization factors, stress states, and live deformation maps. Automated alerts ensure that action is taken before problems escalate. What does this mean for asset owners? No more surprises. Problems are anticipated, not discovered too late. No more costly downtime, precise data-backed maintenance decisions. No more guesswork, a self-learning system that evolves with the structure. WeStatic's 𝗬𝗄𝗃 works extremely well in complex applications as well. The 𝗂𝗶𝗴𝗶 is a critical bottleneck on the Brenner route on the European Scandinavian Mediterranean corridor. The bridge exhibited severe problems with its center cantilever bowing down by 30 centimeters. After extensive structural retrofitting, the bridge still didn't perform as predicted and expected. It was instrumented with a very complex array of sensors and total stations to closely surveil and monitor the structure. A dedicated team of engineers will pore over the data every week and perform assessment calculations to determine the status quo and to ensure operational safety. We were able to save the engineering team 2,000 man-hours per year with our platform. The results they're getting now are faster, more reliable, and exhaustive than their previous methods. You can compare this advancement with the leap from replacing a warehouse full of human computers with an actual electronic computer. One of Milan's main arteries is the 3-kilometer 𝗂𝗶𝗴𝗶 viaduct. It's emblematic for Europe's in-place infrastructure. Built in the 1960s, the aging structure showed alarming deficiencies and had to be taken out of service due to safety concerns. In order to assess its actual physical state, a network of sensors consisting of distributed optical fibers, accelerometers, and clinometers was installed and coupled with our platform. Then a live load test was performed, placing 6 30-ton trucks strategically across multiple spans. WeStatic's predicted deformations with near perfect accuracy, AI-driven calibration adjusted for variations in pier heights, identifying a 20% increase in deflection for taller piers. We could also identify capacity reserves and allowed the operator to reopen this vital structure. Without this validation, the viaduct would have still been kept close to traffic. Another anecdotal result from clients includes the accurate detection of an overloaded, exceptionally heavy transport that passed over one of our monitored bridges. We were able to pinpoint the exact timing of the crossing, determine its impact on the structure, and identify the actual gross weight of the passing truck. WeStatic's 𝗬𝗄𝗃 is the first simulation-based high-fidelity digital twin that's commercially available, and we are certain that we will change the rules of asset management with that. However, setting up such a digital twin is highly complex and requires domain knowledge in a variety of fields. That's why we would like to share an exclusive sneak peek into our latest module, the Twin Builder. This tool will enable any bridge engineer to set up such a twin on the fly, building on FE models they already have in most cases. This will democratize high-fidelity twinning and change the entire 𝗬𝗄𝗃 game. So you will just simply import your finite element model from your standard software. Then we have a very user-friendly interface to place the sensors with their orientation on your structure. So once you're done setting up all your sensors, you will go to calibration, and it will ingest all your measured data that comes from the sensors and then recalibrate the finite element model. And there you go. There is your fine-tuned digital twin at your disposal. And then you can run all your simulations You can assess the true state. There's also an automatic dashboard that it's set up with the twin that allows you to drill down in all the historic data and to do your projections. You also have the ability to export your twin via IFC to use it on other BIM applications, for instance, or have a complete structural analysis at the push of a button. So here we are at the end, and we're ready for your questions. You should be able to turn on your microphone if you have input and feedback for us.
Sorry, can you hear me?
Yeah, I can hear you.
Yeah, I have a question if I can. So your toolbox is able to handle with uncertainties in the measurement. So in which way your toolbox is able to take into account this kind of issue when you are dealing with a monitoring system?
Okay, so it's a multi-layered approach. There's a lot of statistical evaluation that goes into it. So we weed out sensors that definitely send faulty signals. So they're not getting ingested into the system. And then all the sensor data that gets ingested in the system will also undergo a plausibility check. So with all the iterations and inverse analysis, we can weed out faulty sensor data. So the sensor data doesn't make sense, or there's no fitting solution based on the calibrated parameters. And that also gives us a high degree of certainty that certain data is invalid. Does that answer your question?
Yeah. You answered me. Thank you so much.
Let's see in the Q&A. Okay, so let's go through the Q&A. Some people posted there. So here's the question from Pierre: is the system replacing engineers? Of course not. And with AI in general, it's never about replacing anybody. It's just making their work more efficient, faster, and more reliable. So it will still require an engineer. Of course, you get the information about your system and the state of your structure in a much easier and digestible way, so that person that's not a bridge engineer will understand what's the overall condition. But then to dig deeper into failure mechanisms, or where are the exact problems, drilling down, what's the tension in a certain tendon, yeah, that's still be done by an engineer. But this is a system that where traditional methods would take weeks in iterations, it does this in seconds, and so it just becomes much more efficient. And through the Twin Builder, we enable many more engineers to actually use these digital twins. Then we have Mata. Thank you. Would like to know how much does it cost? Okay, here's the question about cost and compared to traditional monitoring systems. So actually, it's not an additional cost. So this software will, in most cases, be as expensive or inexpensive like the software you would get with your traditional monitoring system. So you would not have to invest more money than you do with traditional monitoring, but you're getting a lot more out of it. Okay, let's see if there's anything else. Okay, so there's another one. What happens if the system goes offline? Of course, we're using edge processing, and so all the data will always be stored in situ, and then will be retransmitted once the system goes online again. but you will see it in the dashboard. So there's a monitoring of all the sensor availability and accuracy, and what's the level of accuracy. This is monitored constantly, so you'll be immediately alerted to the fact if some of the sensors became offline, and then you have a chance to intervene. Okay, there's two more questions. How long does it take to fully implement the system on a bridge? And how many bridges are currently monitored? Okay, so the implementation time depends on of course, the complexity and how many times have we seen this particular structure before. So it could be between 3 to 4 weeks, maximum a month. But with the twin builder, this gets even cut down further, so that you can say, if you use the twin builder end to end, it's probably a week. Now, how long does it take to calibrate the model? It's also a very short time. Usually it requires only like about a week of consistent data to calibrate the tool. How many bridges are currently monitored? We have about 400 bridge structures right now in our platform. Okay, there's some more. Okay, maybe one point to stress is that the sensors are an integral part of the digital twin. I assume the reliability of the digital depends strongly on the reliability. Yes, of course. So there is a strong correlation between the reliability of the sensor data, because that's the key. One of the key aspects we've seen what's a true digital twin is that it gets continuously synchronized, and in order to assess the actual physical state, we need this data, and this needs to be reliable. But that's also something that is unique to our platform, because we can tell right away if the monitoring, if the sensors are off, if they're delivering wrong data, and also we'll be able to actually cut down the amount of sensors that you actually use, because we can optimize this. Okay, is it necessary to using SMEs to calibrate the model or not? Okay, so of course, like I said, one part is the operational model analysis. So it would be always best to have accelerometers, but we have done the calibration also using other types of sensors. So basically, the system is sensor agnostic. Are there specific types of structures or characteristics that make digital twin system users particularly suitable? No. So it's not just for bridges. Of course, that's our main focus, but it can be applied to any type of infrastructure, anything that I can model with finite elements and have some sensor data can be used in our platform. There's another question. What is the main difference between WeStatiX 𝗦𝗫 and so-called data-driven systems? So data-driven systems, and if you would like to use data-driven systems for forecasting or to make predictions using AI, this would require the system to see thousands of failures of that type with exactly the same boundary conditions. So they would need to be the same bridge, same environmental conditions, and then see it so many times to be able to predict. And with our simulation-based approach, that's also underpinned by physics-informed neural networks, we do an inverse analysis and simulate until we get the right condition to match all the variables. So we don't need to see thousands of the same failures and able to predict the 1001. Okay, there's no more questions. And looking at the time, we're a little over, so that's fitting too. So thank you again for participating, and invite everybody to join us for our next webinar, where we talk about geotechnical monitoring, where we can also apply our software. And also we're starting taking pre-orders for the Twin Builder, so whoever is interested in that can also drop me an email and reach out directly to me or through LinkedIn, and I'm more than happy to be in touch with you. So if there's no more questions, I would like to close at this stage and wish everybody a productive and pleasant afternoon. Thank you.